let's look at where we're going to go today to get to that point. Our learning objectives for day 2 here, what we're responsible for, is to express the mathematical relationships between W, V, and M. We wrote these down last time, and we use them for the what's called the graphical approach, to draw the V and the M diagram, is where we don't have to make cuts necessarily to find the equations and then plot the equations. We can do the graphical approach, which is to use those mathematical relationships. We need to be able to find the location of zero shear and therefore max min bending moment, and understand what situations result in V is equal to 0 and M is equal to 0. We'll go through all of that stuff here today. So let's start with a review of the graphical approach. Now, this is the exact same thing that we wrote down last time. And so we said to go from, we want to go from the FBD to the V diagram. Then what we do is we say, okay, well, we know the slope of V is equal to W. So that's one of the things that we can use. Then the other thing that we know is that the change in W, or change in V, is equal to the area under W. We also wrote down, so there's really just 3 key things here: a concentrated P causes a jump in V. So those are the 3 things that we need to know, the 3 mathematical relationships that we can use for the graphical approach to go from the FBD to the V diagram. Now, how about to go from the B diagram to the M diagram? So then once we get the V diagram, we can go into the M diagram. And they look very similar to those 3 relationships for the first 3 that we wrote down. Instead of the slope of V, we're going to say the slope of M is equal to V. Now, instead of the change in V, we'll say the change in M is equal to the area under V. And then the concentrated M causes a jump in the M diagram. So those are the ones that we wrote down last time. That is really everything that we need to figure out to do the graphical approach, is to use those relationships, and then we can solve our homework problems. And we wrote this down last time, but I think it's important that we write it down again. So like for our homework problems, homework problem number 1, we just have a concentrated moment on there. Let's look at, actually, before we look at those homework problems, this is the document that is in hands-on number 6. You can access it through the recitations page on Canvas. There's a PDF. This whole document is up there. And also, hands-on number 6 is available through the end of the semester, and you have unlimited attempts to do it. It's 100% remote. You don't have to go to the recitations even to do it. I would recommend doing it before exam number 3, because this topic will be on exam number 3. It'll also be on the final exam as well. So for a simply supported beam, this is the one that we did last time. We have this simply supported beam, and what we came up with, here's our FBD right here. And so here's our FBD right there. So go and look at this document. Well, our V diagram, it starts at AY right there. It's got a slope equal to minus W, and it ends at minus BY. Now, why does it end at minus BY? Well, I talk about it right here. It ends at BY because V is equal to minus BI when X is equal to L. When we're all the way over here at X equal to L, remember X of 0, we are always going to start X equal to 0 at the left end. But V ends at BY because at X equals L, and we can draw a little FBD to the right of a cut there. And we see that when X is equal to L, well, what happens to this distance? This distance goes to 0. And so V has to be, when we draw V positive, it's going up, but it has to be equal to a negative when we sum forces in the Y direction. And so we see it ends at that negative BY. Now, so we use the FBD up here, we use this FBD to figure out what this looks like. And now we can use this to figure out what this looks like down here. We know that the M of 0, we have to know where this starts. So M is equal to 0. And the reason is because the left end face is allowed to rotate in. The left and the right end faces over here do not prevent rotation. And so take a look at this document. Go through that, that hands-on activity to help you out. Maybe even as you're working through the homework, you can refer to this. Let me go on to, how about now if we only have a distributed load over part of it, which was actually our quiz today. And so we see V is equal to AY over here. It starts at AY. The slope is equal to minus W over this region where we have a W. And then the slope is equal to 0 because W is equal to 0 right here. And then it still ends at V is equal to minus BY. Our moment diagram looks very similar here, except that in this part, we have a constant slope because V is a constant. So V it's still a negative value. And so our slope is still negative, but it's a constant negative value. Where in this part, our M starts with a positive slope because V is positive. And then when V gets to 0, our slope on M gets to 0 because V is equal to 0, where that means where our maximum is. And then our V value becomes negative. And so then we see our slopes start to become negative there. How about, and actually we'll do this, we'll jump into this example here. We'll go through this whole thing, but can we use our graphical approach, our mathematical relationships to figure this out? Well, starting with our FBD, then we can find our AY and our BY values. Well, it's going to start with V equal to AY. Notice the slope is 0 because W is equal to 0. And so then we just have a constant slope there. P is going down, so we end up seeing a jump going down, and we get to a V is equal to minus BY. And then we can use our B diagram to come up with our moment diagram. Well, what our slope, well, first we have to figure out M is starting at 0. Again, those end faces are allowed to rotate in. There's nothing preventing rotation. So our moment at that point is 0. And then we see our slope is equal to V, which is a positive AY. So we get a constant slope the whole way. And then all of a sudden our slope becomes negative for the rest of that segment right there. How about with the concentrated moment? Oh, wow, look at this. This is almost exactly the same as your homework problem. So take a look at that one. And then this document, we go into another case with a fixed support now. The idea of this document is that we can think about this logically in terms of, thinking about like, where is tension? Well, in this case, our tension is going to be on the top and our compression is going to be on the bottom. Doesn't that mean we should have a negative moment? Well, how do we figure out that our shape looks like that? Well, we figure it out from our V diagram because we know V is going to start at AY. Our slope is going to be equal to minus W. Over here at this end, we're going to have V is equal to 0. And then our moment diagram, we need to figure out, oh, well, it's negative because we have tension on the top. And that's a negative moment. So we start with the negative moment. And then our slope is equal to AY, but look what happens to V. V is getting smaller and smaller. So our slope gets smaller and smaller as we go up eventually the point right here where we get to a slope of v equal to 0. Okay, so a lot of stuff going on, and that's why we have all these cases written down for you. That's why it's a hands-on activity, so you can get some really nice practice with this to help out with the homework. Here's one of those homework problems right here. Oops, there it was. There it is again. Here's one of those homework problems right here. Take a look at that. Here's another one. How about when we have a fixed support, a distributed load, and a concentrated force? And then here's one with a combination of loads that we have on there as well. So let's jump in and let's look at now some more. We have that document, and you all can look at that. That's part of that hands-on activity. But now let's jump in and let's take a look at going through one of these examples in detail here. So if we have let's look at a simply supported beam here. So I'm going to have a pin over here at A, and we'll have a roller over here at point B. And then we're going to apply a concentrated force of 1,000 pounds, you can call it P, is equal to 1,000 pounds, and that's going to be located at a distance of 4 feet and 6 feet from A and B. We are asked to find, for this problem, the equations V of x and m of x. They also ask us to plot the diagrams for these as well. So we want to find v of x and m of x and plot those diagrams. So for our solution, and let's leave some room, what I'm going to do is I'm going to stack our FBD, and then right below that, we're going to go the V diagram, and then right below that, we're going to go the M diagram. So find a spot on your paper where, maybe you have half a sheet of paper or enough room to stack these on top of each other for our solution. And this is how we typically do it in practice, so that we know where is M max relative to the actual FBD, and where is V max, and where are all the key points relative to our actual physical beam that we are going to use the shear moment to design this. And so let's draw our FBD up here. And so there's point A right there, and then we'll make point B over here. At A, if it's a pin, we would have an AY, and we would also have an AX. AX is going to be 0. At B over here, we would have a BY, and then we have our P equal to 1,000 pounds, and that's occurring at a distance here of 4 feet, and then we have a distance there of 6 feet. Now, if we solve this, we could do some of the moments about A. We would find that BY is equal to 400 pounds, and then we could sum forces in the Y, and we would find that AY is equal to 600 pounds. So we have our FBD, right? The FBD is our first thing. We need to find our support reactions. And then right below that, let's put our V diagrams and our M diagram. So we'll have our V of X will go right there. So this will be our V, and this is going to be in units of pounds. And then right below that, we'll put our moment diagram, and that's going to be in foot-pounds for the units on that moment diagram. And then we'll show our X increasing off to the right there. And our V diagram and our moment diagram can have both negative and positive values. So I'm putting my X-axis kind of right in the middle on there to leave room for positive values for V and negative values for both V and M. So if we want to solve this problem, we can do we can already right now, we can do the graphical approach. Our graphical approach, we use the FBD. And since AY is 600 pounds, I know that my V is going to start up here at 600 pounds. So V is going to be equal to AY to start with, right there, because it's like a concentrated force. It's telling us go up and start at positive 600 because AY is going up. And then my moment, or if I look at my FBD over here, my W is equal to 0. So that tells me that my slope is going to be equal to 0. So the slope of this whole thing is equal to 0, and it's because W is equal to 0. I don't have a W, so my slope is equal to 0. Now my P of 1,000 pounds, it's going down, so I'm going to jump down by 1,000 pounds. That's the relative change that I get. So I'm up here at 600, so I'm going to drop down. I'm going to jump by this P. So we're going to go down by this P equal to 1,000 pounds. And so that's going to put me down here at what is my V going to be right there. My value of my V is going to be a minus 400. And then I'm going to be constant the rest of the way. And so we see those locations where we have change in loads, where we have concentrated forces, we need to show, let's show that those all line up on this diagram. So we can show, what if we just do a dashed line right here, and that shows you where that P is located precisely relative to our FBD onto the V diagram right there. And then we see this slope is equal to 0. Slope is equal to 0, and it's because W is equal to 0. And so that means our V right here is going to end at a minus BY, or a minus 400. So there's our V diagram. Our M diagram, we will go from the V into the M. But we do have to figure out where we're starting. M is going to start right here at 0. M is going to be 0 because it's a pin at the end of the beam. So M is 0 right there because it's a pin at the end of the beam. Those end faces are allowed to rotate in. We get the foam beam here. Those end faces, they're allowed to rotate in. So the lines are not getting closer together or further apart. Now, if I don't allow them to rotate, if I have like a fixed support, now you see we get tension on one side and compression on the other. And so that means we do have a moment right there. But at the pin at the end of a beam, we don't. And then our moment diagram is going to have a positive slope because our V is positive over this first region. So our M is going to go like this. We're going to get to that spot right there. And now all of a sudden our V diagram goes to a minus 400, or a negative slope. And so then when we get to the end of the beam over here, from this point to this point right here, we're going to have a negative slope over that whole thing. And we should find that we get to an M equal to 0 because it's a roller at the end. And for the same idea of M equals 0 at the pin at the other end of the beam, we end up with M equals 0 to roller at the other end of the beam. Our slopes here, right here in this region right there, our slope is equal to a positive 600 because it's equal to the value of V over that region. And then right here, our slope is equal to a minus 400, which is the value of V over that region. Now, how do we figure out M max? So how do we find this M max value right there? What is that going to be equal to? Well, we can use our other relationship. We know we haven't used, we could have used it in drawing our V diagram, but the area under W, the change in V is equal to area under W. Well, what's our change in V? We didn't have any change in V, right? Our slope was 0, so our change in V was 0. Well, let's use that same idea though for our moment diagram. The change in M is equal to the area under V. Well, what's our area under V? What about this area right here? Let's call that A1. And then this area over here, let's call that A2. Well, A1 is just going to be equal to the 600 pounds times 4 feet. It's just the area of that rectangle. So 2,400 pound feet. That's the change in M. So we start at 0. That means that M max is equal to 0 plus A1, or 2,400 pounds. We can do A2. A2 is a minus 400 times 6 feet. And so we have a minus 2,400. Well, that's the change in M to get to the end here. So we start from, M at B is going to be equal to our M max minus A2, or a 2,400 minus 2,400 equals 0. And so we see that those change in M's are also confirming that M is equal to 0 at the right end there. So that's the graphical approach. What about the equation? We haven't come up with the equations yet, right? It asked us to come up with the equations. Well, could we come up with the equations just by looking at our diagrams here? Wouldn't V, there'd be one equation for V from 0 to 4, and isn't V just a constant? It's equal to plus 600. And then how about from 4 all the way out to 10 feet? Wouldn't V just be equal to minus 400? And then couldn't you then figure out the equation for this M right here and the equation for this one? Well, let's look at developing those equations using cuts. How about let's find V of X and M of X using cuts. Well, how many cuts, how many different equations do we have? We have 2 different equations, don't we? We have a cut 1 is going to be we have an equation from 0 to 4, and we have another equation from 4 to 10. So we need 2 cuts. And so we're going to have cut 1 is going to be valid from X is equal to 0. And I'm going to say all the way out to 4. That P is a concentrated force. So we technically have 2 equations right at X is equal to 4 feet. And so both of them are going to be valid right at 4. So X goes from 4 and then all the way to 10. Well, let's draw an FBD of cut 1. So cut 1, and I'm going to go to the left. So cut 1 is this segment here. It's before we get to P. So the only thing that we're going to have on there is our AY equal to 600 pounds. Technically, I guess we have an AX, which is 0. And then notice no P, but we will have our positive internal forces. So we're going to have a V of X going down, which is positive for V when we're going to the left of the cut. M of X going such that we have tension on the bottom and compression on the top. And then we would technically also have our N, but we really don't care about N. I'll still put it on there. And this cut is going to be at a distance of X. And remember that X equals 0 is always at the far left end. So from this cut right here, which is, this cut is valid from 0 and including 4. We technically have 2 values, like right as we're kind of approaching P, but like including that 4, but without P on there. And then we'll have one where we're going past that location of our applied concentrated force P. And so now we have our FBD. We can simply just sum forces in the Y is equal to 0. And what are we going to find? Minus, and let's make positive going up. We have a minus V of X and a positive 600. That's everything in the Y. And so we're going to find that V of X is equal to a positive 600. That's the same thing we found when we drew our diagrams, isn't it? We just had this constant positive 600 there. Now, how about summing moments? We always sum moments about the cut. It just makes our life easier. We have our positive sign convention for summing those moments, which is counterclockwise. So we're going to have our M of X, and we're going to have also a minus 600 times X equals 0. So we're going to find M of X is equal to a positive 600X. So there's our equation. Actually, what's our equation? It's at X equals 0, M is equal to 0, and our slope is equal to positive 600. That's that same thing that we got when we drew our moment diagram, isn't it? We got M equals 0, at X equals 0, and there's a positive 600. What if we plugged in X equal to 4 into this equation? What would we find? We would find 2400, which is our M max, the same value that we found there. Let's now look at an FBD of cut 2. You can go either direction on either one of these cuts. I'm going to go to the right for this one so we can see both scenarios. You can really pick either one. I could have gone, if I go back to my original FBD here with a cut 1 and a cut 2. So there's cut 1 and a cut 2. Notice that I'm showing those cuts right in the middle of my region. And that's how I want to draw my FBDs, like they're showing up right in the middle of those two regions where I have the different equations. And so in each of those cuts, we can go to the left, and in cut 1, if I go to the left, it looks a lot easier. All I have to deal with is AY. In cut 2, if I go to the right, all I have to deal with over here is the BY. But I could have gone to the left also, and then I would have had the P in there and AY, really not that much harder. But let's look at both so we have experience handling both. So cut 2 will go to the right. So there's our cut right there. And we're going to have our BY right here that's equal to 400 pounds. And then we have V, when we go to the right of the cut, V is positive going up. We have M is positive going in the clockwise direction. And I'm not even going to draw N in this one. I kind of crammed my stuff in there. I don't have any room to draw the normal force. But we're not worried about the normal force, so it really doesn't matter. Now, one thing that changes when we go to the right of the cut, though, is that remember, x is equal to 0 is like over here somewhere, right? At point A. This is point A. That's where x is equal to 0. So this distance from here to here is x, which means that what is this distance from there to there? Let me call on somebody in the front row. Lee, I see your camera on. Any ideas what this distance might be here from BY over to the cut?
Oh, sorry, I didn't unmute myself. Would it be like a y plus x?
We can think about it like that. What's this whole distance from x of 0 from A all the way over here to B?
It's 10.
10. Yeah, so that's 10 feet, right? So then what's this distance? If this is x, in terms of x, what's this distance here?
Oh, it just can be 10 minus x.
10 minus x, absolutely. Okay, so that's when we go to the right of the cut and we're doing things as a function of x, we do have to remember to take into account that x of 0 is still over at that left-hand side. So, and even though this is cut 2, which is only valid from 4 to 10, we don't like reset our coordinate system. Our coordinate system of x equals 0 is always on that far right side there. Okay, so now we have our FBD here. We have 10 minus x on there. Now we can, again, we can sum forces in the y is equal to 0. We'll go positive is going straight up. We're going to have BY is 400. It's going up. Plus we have our V is also going up. It's positive for our internal sign convention. It's going up. So it's also positive for equilibrium sign convention. So that's everything in the y direction. So this means that V of x is equal to a minus 400 pounds. So we see, we get a negative from the FBD. And so because that's why when we're always on the right hand, when we go to the right side of a beam and we got a positive support reaction, it always gives us a negative BY, and it always gives us a negative V, because V has to go down in order to counteract with the BY going up. And so, but down is negative for us, right? A V going down is a negative V, and so that's why we end up with a negative shear value at the end there. Again, it's a constant, just like we saw when we drew that diagram. And then let's sum moments. We're going to always sum moments at the cut. We got our positive sign convention is going counterclockwise. Our positive internal moment is actually going clockwise. So it's a negative m of x. And then our by, let's see, that's going to cause a positive rotation. So plus 400 times 10 minus x. That's everything that's causing a moment. So we end up with a m of x is going to be equal to a minus, or let's see, if we move things, it'll be a positive 400 times 10 minus x. So we're going to end up with 4,000 minus 400x. The 400x, the minus 400x, that makes sense because that's our slope, right? And we looked at when we did our diagram over here, we have a minus 400 in this segment right here, right? Our slope is minus 400, and that makes sense, right? There's our minus 400. Also, remember, this is the integral. The m of x, isn't this the integral of v of x? And so that, but the 4,000, what is that 4,000? Where did that come from? Well, remember, this equation is only valid from 4 until this is valid for x from 4 to 10. this 4,000 would be the y-intercept way over here at x is equal to 0, right? But we're not valid in that region, but we kept our x of 0 at a, and so that's why we have that y-intercept in there at 4,000, because the y-intercept isn't something else, right? The y-intercept is over there where x is equal to 0. Okay, so we've done it two ways. We did it the graphical approach first, and we saw that, and then we also did it by making our cuts here and doing it that way. We did a cut to the left. We also did a cut to the right. Let's take a look now. And actually, well, let me stop there. Any questions? This stuff is not always like totally intuitive and obvious. The hands-on activity is intended to make it more intuitive, because we can't think about this intuitively. Like, where's the tension? Is the tension on the bottom or the top? Right? Like, this whole thing has positive moment. Well, that means all the tension is on the bottom over the whole thing. And we can think about how the deformed shape would create that and have that tension all along the bottom. But remember, we're doing two different approaches here. Let's look at another problem here. How about a fixed support problem? So we've done a couple of problems with pin and roller supports. What about a fixed support? We're over here at we have a fixed support on the right side there. So B, this is going to be a fixed support. And then we're going to apply a distributed load over that whole region there, over the whole thing. Let's take W is equal to 50 pounds per foot. And then we're also going to have right here a 200 foot-pound moment, a couple moment that's applied right here at point A. And A, this is just a free end. This is like the diving board. A is like the end of the diving board. It's just hanging out over the water there, nothing supporting it, but we've applied 200 foot-pounds at that spot right there. And so what we want to find for this is, let's just do the diagrams, the V and M diagrams. For our solution, let's stack our FBD and then our shear and our moment diagrams. So we'll put the FBD right here. So we have point A, and I'm just going to do a wireframe, and then point B over here. Actually, let's give it some dimension so we can think about where the tension is going to go for our moments. And then right below this, let's put the V diagrams and the M diagrams. So we'll go and kind of show some reference lines on here. Oh, I might need some more room. Just leave some room below. Before we put the V and the M on there, let's put everything on our FBD up here. So there's our distributed load W. We have an applied moment over here of 200 foot-pounds. At the fixed support B right here, we will definitely have a BY. We will definitely have a BX. And then we'll also have a moment. And I'm going to draw the moment here I would find if we solve this FBD, we're going to find that BY is equal to 400 pounds, which is just the 5. Oh, and I need a distance across here, don't I? I forgot about we need to know what that distance is right there. That's 8 feet. And let's put it over here as well. That's our 8 feet right there. So I got that 400 pounds by taking our W of 50 pounds per foot and multiplying it by the 8 feet. So we get to 400 pounds. Bx is going to be equal to 0. There's no horizontal forces. And then my moment for it to, my moment is actually going to go this way. So my MB is going to be a 1,800 foot-pounds. And so I'm not going through this process of solving for all that stuff, but we need to do that, right? We have to find those support reactions, but we should be really good at finding all those support reactions now. Now let's put our V in here. So that's where we're going to put V, and this is in pounds and units of pounds. And then right below that, we can put our M. And actually, if you think about this, are we going to have for our M here in units of foot-pounds, where are we going to end up with our tension? Is the tension going to be on the bottom? Remember, tension on the bottom is a positive moment. Tension on the top is a negative moment. Well, if this is a fixed support right here at B, then isn't this going to go down like this? And where's all our tension going to go? All our tension is going to go across the top, isn't it? So it's going to be a negative moment. So I'm actually going to show, I'm thinking ahead a little bit here. I'm going to show my x-axis close to the top of my moment diagram, because actually this is going to be all negative moments. My shear here, I'm going to show it kind of closer to the top as well. My shear is actually going to be all negative also. But that's something we really really don't have to worry about it. But for doing this example in class, to make it look nicer, we can move our axes, the x-axis, up a little bit closer to the top of that V and M diagrams. Okay, where are we going to start it? At point A right here. So we have point A and then point B. At point A, what do you think the value of the shear is? Is there a support reaction there? There's no support reaction. There's no applied force. And so we're going to start at A. Our V is going to be equal to 0. The couple moment does not affect it. The couple moment will affect the moment diagram, but it will not affect the shear diagram. And then we see, so there's no concentrated force at A. There's a distributed load, which tells us our slope, our distributed load is going down. So our slope is going to be equal to a minus 50 pounds per foot, that whole way. And then our V at the end over here is going to be equal to a minus 400 pounds. We have a BY going up, it's at the right end. And so for that BY to go up, our V has to go down right there, which is a negative V if we're looking at an FBD to the right. So our V would be equal to minus 400. Or we could also think about the change in V, right? Our change in V would be the area under W. The area under W is 400 pounds. You can think about it that way as well. I just realized it is 1:50. Why don't we go ahead and we'll finish this example next time, and then we'll be finished with V and M diagrams. You all have a great